Hello, my name is Zakaria. I'm a PhD student in ETS Montreal, University of Quebec. I'm making this video to give a demonstration on the project work for the Network Softwarization course. This project was individual project. The topic for this project is Synchronization-Aware Patterns. As a part of this project, we have studied some literature works in this area as theory and also done an implementation on the proposed area. Network function visualization. The concept is to decouple software from the hardware, leveraging visualization technology. These VNF basically run on virtual machines which are hosted by commodity servers in what is called virtual network function. Therefore, network function visualization is considered as a way to decrease cost and accelerate service deployment for network operators. One of the main challenges related to the service request provisioning is to find the most appropriate placement for a service request that is composed of multiple instances, taking into account the request requirement in terms of bandwidth and resources. Also, several studies addressed VNF placement and chaining and assume there is no synchronization cost between VNF instances of the same type, which is not realistic since most VNF are stateful and this state need to be shared across VNF instances. Therefore, data synchronization must support access to shared state in a manner that ensure the consistency requirement of the state are met. From this figure, we can see that we have a physical infrastructure, and this infrastructure has multiple POP. Each POP consists of multiple servers, switches, and routers, and they are located in different geographical location. VNF are set up on top of commodity server and placed in POP like this. So POPs are heterogeneous and located in different locations. This means that the resources of each POP different than the other. Virtual network function in each service function chain may consist of one or more instances of the same type. Like IDS, for example, has 3 VNF. The number of instances to each VNF vary depending on their processing capacity. Once the requirement of the service request are defined, the service provider will be responsible for assigning resources for this VNF into physical infrastructure. The synchronization cost between VNF instances of the same type can be high by placing them on different POPs that are located in different geographical locations. So we can see here we have 3 VNF instances for IDS. One it's placed on the POP 8 and the other placed in POP 9 and 11. If one of them need to synchronize its data with the other, we can see we have multiple hubs. The reason for this increase is that these VNF instances need to share information between them to establish consistency and harmonization over time, and these instances will use multiple hubs. So, we proposed a solution to minimize the synchronization cost between VNF instances of the same type. We consider implementing synchronization patterns that are tried to minimize the synchronization cost. Each pattern has different technique to calculate the synchronization cost. The first pattern is the minimum spanning tree. After implementing a Prim's algorithm on the previous topology, we will get this graph. This graph is the minimum spanning tree. The cost of the spanning tree is that sum of the weights of all the edges in the tree. There can be many spanning tree. Minimum spanning tree is the spanning tree where the cost is minimum all the spanning tree. Let's suppose there is VNF instances want to synchronize its data with a set of VNF instances of the same type. To keep synchronization cost down, we could connect these VNF instances with the spanning tree based on the number of hubs, as we can see here from this graph. In the minimum spanning tree pattern need not to be path. It can have branches. Therefore, each VNF instances is directly connected to all other other VNF instances of the same type that are located in different branches, which mean we have VNF in the POP 1, and this VNF need to synchronize its data with the other VNF instances. Okay, so this VNF can communicate with the VNF that located in the branch 2 in the POP 5 and located in the different branch 3 to communicate with the VNF 1 that are located in the POP 13. Which means, therefore, each VNF instances is directly connected to all other VNF instances of the same type that are located in different branches. The second pattern is the full mesh pattern. We will get this graph after implementing the full mesh pattern. Each VNF instances is directly connected to all other VNF instances of the same type in the physical infrastructure, which means appropriation of VNF instances in this type of pattern have multiple paths to another VNF instances. Therefore, a major advantage of this pattern that determine the best route to destination. In other words, if the VNF instance 1 in the POP 1 that want to synchronize its data with the VNF instance in the POP 5, this instance has two routes. So this instance will go with the shortest path. The VNF instance that want to synchronize its data can choose best route to reach the other VNF instances of the same type based on the minimum number of hubs. How the code work? First of all, we have to load the topology, then generate random service requests. In our code, we generate 200 service requests. After that, we have to load the scenario. We have 8 scenarios, as we can see here, and each scenario represents a different way to embed the service chain. In other words, we change the number of VNF instances embedded in each POP for each type of VNFs. For example, node 0 has 8 types, type 1, 2, 3, 4, 5, 6, 7, 8. The VNF instances in the type 1 is 0. The VNF instances in the type is 6, it's 1. After that, we have to distribute the VNF instances on the VNF type. After that, we have to get the patterns, the minimum spanning tree pattern and the full mesh pattern. Finally, we have to calculate the synchronization cost between VNF instances of the same type and synchronization cost for the service function. Let's go to the code. Okay, let's go through the functions. Okay, we have here some functions. The first function is the function that responsible for generate the service request. After that, we have function to load the scenario. In our demonstration here, we will present the scenario number 8. So we have to read the data from this scenario, like capacity, utilization, the number of instances for each VNF type. After that, we have function to calculate the number of hubs between VNF instances of the same type. We used here a breadth first search to visit all the POPs. After that, we use the union disjoint method to calculate the number of hubs between VNF instances of the same type. Okay, we have also function that's responsible for distribute the instances on this VNF type. The distribution, it will be done randomly. This function, to get the minimum spanning tree pattern, we get the minimum spanning tree pattern using prems minimum spanning tree pattern. After that, we have the function that responsible to call the distribution function to assign the VNF instances for each type. After that, calculate the synchronization cost for each VNF type. Like this, for example, synchronization VNF type 1, it will be called this function to calculate the synchronization cost for the VNF type 1. Okay. How we're gonna calculate the number of hubs? It will be explained here. Yeah. So here, for example, how we're gonna calculate the synchronization cost for VNF type 1. Okay. First of all, we have to store all the bobs that contain the VNF instances in the vector and call the function that responsible for calculate the number of hubs. We can see this function, it's here. Just a second. Yeah, this one, the total node. So we will call this function to calculate the number of hubs between two instances. After that, we're gonna use the same way to calculate the synchronization cost for the second pattern. It's the full mesh pattern. We can see it here. Where is it? Yeah, this one. This function to calculate the full mesh pattern. Let's run the code and see some results. Okay, after running the code, we will get here some text file. Okay, so first of all, the service function chain. We have here 200 service requests. Each request has different VNF type. 0 means there is no this type is not available here. 1, that means this type exists. After that, we're gonna get the pattern, minimum spanning tree pattern. This one, for example, no Bob 0, it's connect with Bob 1 and Bob 2 and so on. The full mesh pattern here, that means Bob 0, it's connect with 1, 2, 7 and so on until Bob 13. So now this is the scenario number 8. As I mentioned, for example, node 0 has capacity 40, utilization 22. For example, we have 12 instances placed in the Bob 0 and so on. Okay, now here the distribution. For example, service function chain 1 has 3 instances. For VNF type 3 has 17 instances for type 16 and so on. And the result here for the minimum spanning tree, we can see service function chain 1 has 0 instance for type 1, 0 instance for type 2. The synchronization cost is 0 for VNF type 1. Synchronization cost is 0 for VNF type 2. Synchronization cost is 34,500 for the VNF type 3. And here the synchronization cost for the service function chain. This one for the minimum spanning tree, and for the full mesh pattern, we can see also this result. So if we're gonna compare between the two patterns, we can see the minimum spanning tree, for example, the synchronization cost for the service function chain is 760,500, and for minimum spanning tree is 51,500. Thank you.